Otherwise, you can go for a time sharing mode, because many students, I find that they're leaving in between the class. So you can prepare some schedule who will leave and who will join, and make the figure not exceeding 100. That can be one possibility. 95. Okay. Now, what we are discussing, as I mentioned, so this is very important, because these files are something uh, we always need to deal with. And this is the details of the outline of how the files are handled by the system, and how the users also keep track of their files, and how the system keeps track of the different files opened or created by different users. And that's the case. So every user has got one file table descriptor corresponding to all the open files, and these are the trivially open files: stdin, stdout, and stderr. And the nice thing in Unix is it handles even the pipes, the sockets are also treated as files. Okay, so that's a uniform way of handling things. Anything that is related to input output, or communication with other processes, or communication with other processes which are in other machines and all this. So that is to have a uniform way of handling that has been done. So this is the xx.text, which is some other file, just having some text or binary here. So this is the system-wide file, which has got an entry corresponding to each of these files, uh, each of the files opened by any of the processes in the system. And say if a particular file has been opened in the read mode, and it has been opened in the write mode, it will have two entries. Okay, the same file xx.text, open in the read mode and the write mode, it will have two entries. Okay, so it might happen that there are two such entries in the system file table, which points to the single node here. I mean, single say entry here, because the files inode is this, the physical say copy of the file is here, but the file, this is in the read mode, it's accessing maybe some other process, it has opened it in the write mode, so in that way it can work. At the same time, there may be it may happen that this file descriptor of this process, uh, it is pointing to it. There may be multiple processes pointing to this, the same entry. We'll come to that. Okay, but the interesting point is this file descriptor count. It is like how many file descriptors, or in other words, you can say how many processes are referring to this file in the read mode. That count is here. In this case, it is just one. We'll see shortly that when, in, and how, in what case it will be, it might be 2 and 3. Offset is the pointer, the logical file pointer here, which keeps track of how many, I mean, what is pointing to, what is the next character you are going to read. And then it's in the read mode, means you can only read through the file descriptor if you are pointing to this one. If it was write, means you can also write here also. It can be read write or append mode. So all these are possible. Okay. Now, one more important point is, so like these are the files, these are the, so everything here, as you can see, this process table entry, the U area, the kernel stack, the segment map table, the page map tables, everything here, including the system-wide file tables and all this. So these are all so although they are related to the process, but they need to be maintained in the kernel space, right? Because these are all something that a process should not be allowed to access or to modify it in the user running mode. Otherwise, it will be dangerous, because you will be doing maybe harm to yourself or maybe to others also. So all these information need to be stored in a different space, which you can say term it as a kernel space. However, when this the actual code or the stack segment, user stack or the heap, they all belong to the processes, say user area, because the process itself as the user has written and the user wants to do something. So that's the case. So if we consider, say, till now we are talking about virtual address of a process. I think you can recall the diagram. I stick to that diagram. So virtual address or the user space of the process. So here we have got the code segment, the data segment, the stack segment, and the heap segment. So these are all many a times we have talked about this. Now the point is what this actually refers to. This virtual address space, does it include the kernel, say kernel level space also? This virtual space, this includes the processes, code, stack, and all this. So this, does it include the kernel tables and all? Hello, are you getting me? Does it include anything about those data structures that we just now mentioned? This is not. Okay, so this is purely the user space. But the point is, when we say that a process is running, so a process is running, and because of virtual memory, if the total size of the RAM is 4 GB, then the virtual space size of the entire process should be 4 GB. So the process, logically, a user should think that the process is as big as 4 GB. Now the point is, this 4 GB space is logically fragmented into two parts, or logically divided into two parts. If you consider this the 00 address, the increasing the address, virtual address is increasing this side. So this is the virtual view of the process space. So this is the 00, the lower order locations, of the memory locations, and then from 00 to say up to
Sir,
this. Yes,
sir, the problem is coming again, sir.
again coming.
Yes, sir.
Okay,
100
see.
participant and you one host.
Yes, so the I'm sure the problem is problem has triggered, so it's no longer free to use, and it will persist. So I understand it is I should not, so I should make provisions to everybody to attend the class in live and give the scope, but just
Sir,
tell them that I am hmm?
we can use the Microsoft Teams.
Yes,
Our optional electives are already going on Microsoft Teams, so I think we can use that.
Teams I can use, but I have not used it earlier, so this might take some time. So may I continue the class, and I'll send the recording? Is that possible, or they want to take it? Then I have to stop the class. Maybe I can try tomorrow, because
Sir,
Sir,
it's okay, sir. You can finish the class today, I think.
yes,
see,
sir.
I understand, because I should not deprive others also to join, but this is the problem that I faced for the first time. And if I try to switch it, because I have not taken a class, it will take some time. I mean, at least maybe 10 minutes it will take. It will waste some more time. And because we are having the recording, I think they still can listen to it, and I can have maybe 5-10 minutes time to take their questions if they have any doubts. So that's the point. And then don't worry about the attendance. Let them assure them that they do not have to worry about the attendance right now, because of these issues are there. I'll resolve it by the next class. So may I continue, or I mean, what the class says? Just tell
Yes,
me.
Yes, sir. Sure, sir.
yes, you can continue, sir.
Yeah, just drop them a message, and I'll resolve it by next class. Okay,
Okay,
so
sir.
what we are I'm telling is, in case we have got a 4 GB RAM now, so the ideally the whole process should be able to access the
The
whole
screen
4
is
GB
not
Sir,
RAM.
visible.
actually, the
Yes.
So your presentation is not.
Okay, sorry. Okay, I'm not shared now. Now is it okay? Are you getting the
Yes,
presentation?
sir. Yes, sir.
Sorry, there are a lot of interruptions. So the point is, in a 4 GB RAM machine, so you can think of that the process can access the entire 4 GB RAM. Okay, so if that happens, and this means that the as we just now found that if we think of the process space or the virtual address space, so that should include the user space contents. These are the user space contents where the user has which the user has written, and it wants to manipulate. It's a code heap and all this. But there will be also a portion which is a part of the kernel space related to the process. So this is this one. So in this kernel space, it is not that the entire operating system will be loaded. As and when it is required, whichever module is required, it will be used, but only this much of space. So this is basically 2/3 will be used for the user space, and 1/3 generally, as per the layout is concerned, is used for maintaining or storing the kernel tables and the different tables related to the process, as well as the different kernel modules and all. So that is the layout. So this is we can think of that this is the kernel space and this is the user space, user area. So in the user area, and it has got a specific sequence in which these 4 segments are organized. One is the code segment, then comes the data segment, then comes the heap segment. It grows in this size, and the user stack segment grows in the downward size. So that way they can utilize their space. In a mutual, agreed form. And these are the environment or argument argv, and all this, which is required to initiate, which is passed in the main. And then rest of the part, that means just a minute. So rest of the part, that means this part is the kernel space, which contains the kernel stack, segment map tables, page map tables, view area, then the system file table and all this. Okay. So I think this is the view that the user process or the user itself feels in a virtual memory system. So whenever you get the, say, this is my process, blue process, you may be running the green process. So green process, once it is running, you will think of that the whole it is able to use the entire system RAM. It gets a feeling of it, but it is not actually the case. We know that in reality, parts of this data segment, code segment, even the kernel data structures also swapped and all this. So they are partly allocated, and through those segment map tables and all, they get tracked. And this is typically the situation in a x86, that is Intel based processor, and with operating system which is 32-bit. If it is 64-bit, it will have a much larger space in its use. So if you have got more than 4 GB RAM, you can probably install 64-bit operating system, so that you get access to much larger RAM. Otherwise, if you still install 32-bit operating system, the majority of the beyond 4 GB, the RAM will not be utilized, and it's of no use then. Okay. So now this is the kind of recap part. In today's topic, we talk about the fork algorithm, the details algorithm of the of how to create processes, how to call fork and create the processes. So we just now, in our last class, we last class, we found how we use the fork and how it works, just calling the fork. But today we talk about the internals of the fork algorithm. What are the steps that it follows to actually create a duplicate of a process, a child of a parent process. Okay, and we'll take some examples of fork. So let's get back to this. So this portion, this algorithm, it has been again copied from the Maurice Bach book. There are 2-3 pages, and it nicely explains the philosophy and what exactly need to be done. So if we consider that this is a green process, which is it's already there, let us call it as a parent. Let us see stepwise how a blue process, which may be considered to be the child of this parent, gets created step by step. Okay, so let's see. So the fork algorithm, it as you can recall, it doesn't take any input argument. It takes void, but it returns what fork returns. It returns some PID value, not integer, but it returns some process ID values. And I think you all can recall that the fork, if it is executed, the parent process creates a child process, and both, when the fork is complete, both the parent and the child independently, they feel that they have returned from the fork statement, from the fork system call. So what fork returns? It returns the child of the parent. It returns the child of the parent. So what fork returns? It returns the child of the parent. So what fork returns? It returns the child of the parent. So what fork returns? It returns the child of the parent. So what fork returns? It returns the child of the parent. So what fork returns? It returns the child of the parent. So what fork returns? It returns the child of the parent. So what fork returns? It returns the child of the parent. So what fork returns? It returns the child of the parent. So what fork returns? It returns the child of the parent. So what fork returns? It returns the child of the parent. So what fork returns? It returns the child of the parent. So what fork returns? It returns the child of the parent. So what fork returns? It returns the child of the parent. So what fork returns? It returns the child of the parent. So what fork returns? It returns the child of the parent. So what fork returns? It returns the child of the parent The only way to distinguish is the fork returns a non-zero value, that is the child process ID in the parent, whereas although the new child is exactly similar as that of the parent, but it receives a value 0 as returned by the fork. Okay, so the output will be to the parent process, it is the child PID, the new child got created, and in case of child process, it will be 0. So this is the input output. Now let's see how it is exactly creating the child. So this is it's a check for available kernel resources. So the first thing is, what do you expect? What is required uh, before any child is getting created? First of all, you have to see that whether there are at least few slots are available in case of Unix. In case of Linux, you have to find out whether there are enough memory so that you can have allocation of one at least node, and you add it in the doubly linked list data structure, task structure. So you check for availability of kernel resources, and this is the free to get the free table slot, and you have to also grab one PID, because that is important. You have to grab a table slot, you have to grab a PID. If the PID is not available, then also you can't create a new process. So hopefully those will be available. And because this Maurice Bach book was written in mid 80s, when it was the Unix system, the BSD Unix, the system version 4, these are getting commercialized during those days. It is even before 90s. So that those days it is purely Unix type, and those Unix systems used process tables. They didn't use the doubly linked list data structures. That's why you will find that it's get a free process table slot. So this is not Unix. Unix just does the similar thing, but in a different way. The data structure is different. So, but still we can assume that the philosophy is the same. Now what it runs, what it considers, we also probably we can have some provision to make sure that a user process cannot create say infinite number of processes as its child. Otherwise it will eat up the entire system space. So there can be some limit for that, and there are always some limits which is maintained in the U area of a process. How many files you can create and open, what can be the maximum file size, how many processes you can spawn or create. So all these are there. So if everything is fine, then the child state is created, is marked as created. You can recall those process transition diagrams. So what you can view is, earlier it was a green process, now you find that it has grabbed probably this process table slot, and you have just the state is it assigns the created state, and it has got a PID because it has grabbed its own PID. Okay, so these are child is just taking birth, it's not yet complete. So next step, what is this? Copy data from parent process table slot to new child table slot. So you have to basically copy from the parents table slot everything that is here, directly just copy it here with blank copy, I mean a blind copy. So what we have something like this. So everything that is here, and I have tried to make sure that the color is also the same. So this means that these are different, but these fields are same as that of the parent. It's just like copying. Now what next? Now increment the counts on the current directory inode and the change root. Increment open file count in the file table. What does this mean? So this simply means that if the parent has if the parent's current working directory is say in my case it is say node, or say oops, whatever I mean. So if I create if the parent process creates a child, the child also will belong to the same working directory, current working directory. So that will be the same. And at the same time, as I was mentioning, that in Unix, even a directory also is treated as a file. Okay, it's you can call it as a directory file. So directory entries are also treated as if they are files. So here the directory file entry will be now, earlier it was the parent process, now it will have one more process also associated with it. So the process count corresponding to that directory file will be incremented by 1. Okay, try to recall the discussion that I just did in early in this class. And then increment open file counts in the file table. So this is the offset. But before the offset, we have got the file descriptor count. So that will be incremented, because what it means, the parent, if it has opened, in this case you can see it has opened this xx.txt file. Now if it is going to create this blue child, the blue child also will have access to that file without explicitly opening it, because the parent has opened. Like if your father has opened his account, so probably being a son, being his son, you will be able to have shared access to that account. It's like this, it's kind of default, but it's not actually. You have to be included as a joint holder. But in this case, if the parent has opened some file, it is in the read mode, the child automatically gets access, in fact the shared access to that file in the read mode. Okay, so definitely in that case, this count 1 should be incremented by 2 now, because uh, the child also will be pointing to this one, and that is what is happening. So it has incremented by 2, right? So this is what is done. Next is make copy of the parent context uarea text data stack in memory. Now this is an important task. So what is there? So now you are trying to create the tables for this child, and you have to create the space for the uarea. So this is the next step. So what is happening here is this. You see, from here is here. So now the blue child's tables are also created, uarea created, kernel stack created, everything got created. Now what do they contain? And you just so you don't basically copy the contents here. Rather, what happens here, the contents of the stack code, data segment and all this. So these tables don't actually have the contents. The contents are either in the disk or in the primary memory, but you have got the separate tables which will actually point to the duplicate of those pages. Okay, so the child will have its own copy of them, and they will be maintained by they will be tracked by these tables. But what will be the values of those code segment, data segment, heap segment? It will be exactly that same of the parent, because you are trying to create a copy of it. So the point is, make a copy of parent context, parent's user context in the memory. So we have made a copy of it, and there will be some links here like this, and the uarea. So uarea will be also copied. The contents of the uarea is copied here, and the kernel stacks content will be here, like this. Okay, and this, once it is copied, so this stdin, this xx.txt, these also will be pointing to the same. So this file descriptor of the child will be pointing to this, and this file descriptor of the parent also will be pointing to this. So both will be pointing to the same. Now what next? Next is push the dummy system level context layer onto child's system level context. So that means this is what is happening. So this user level context you have pushed. Why? Because while calling for, the parent process has switched from the user mode to the kernel mode, and because it has switched, so in the kernel stack it has pushed the user level context, so that once the execution of fork is over, it can return back to the user process, to the instructions that it was executing before fork, exactly in that point. So so it will be able to resume from fork. Okay, so now in this step, it basically copies this user level context of the parent also to the child, and this actually makes it possible that both, because both are having the same user level context, as you can see, as a result, when the system returns from fork, both the parent and child, they find that so they are as if they have just returned from the fork. So the child also feels that it has returned from the fork. The parent definitely will feel that it has returned from the fork. So it's exactly copying the user level context. Now what next? Now by this time, what has happened? The kernel, it was executing for requested by the parent, and in that process, apart from the parent, it has created a copy of the parent, and this is the child with this new PID. Okay, so this part is done. Now it is about to return back to the parent and child, so that they individually can resume their execution. So now what happens? There are two processes. Now the kernel decides that if it has so now still it is not going to the user running mode. What it does, if the executing process is the parent, that means if the kernel is considering this process, this is the last step of the fork execution. So if this is the parent, it changes the child state to ready to run, because now earlier the child was created and now it is everything is ready. Everything is ready, even the context, everything is ready. So now it can tag the child to be created and it will return the child ID. It will return means the fork returns, and who will receive it? The parent will receive it, because it is a parent. And where this return ID will be stored? It will be in the U area, because in the U area there is a field which stores the return values of the system calls as well as error calls, if there is error. So these values it will set. So it will do something here. You see, now it is ready. It has made the child ready. That was the last task the parent will do on its behalf in the kernel mode, and the parent also will have the child ID returned here. Then it will copy somewhere else, but it will be copied here. So once this is done, then the kernel takes care of the child process, the blue process. So the blue process, what the child does, the kernel does. Now because so it initializes the U area timing fields. Now when it was created from the, when you copied things from the parent, you copied everything from the parent, even the U area contents. So if you just leave it as it is, what will happen? The parent might have executed CPU for maybe 5 minutes. It was executing CPU statements, and now it has forked a child. If the newborn child was created and it has copied the same values here, so this also here there is a timing field. It will say that it has utilized the CPU for 5 minutes, but this is not the case. So everything you copy, but this U area which stores the timing information and many other informations, so many things you have to initialize for a newborn child. Okay, so this part is done. So that's why, although it was earlier the same green, but now you overwrite it some of the fields and initialize the child's U area so that it behaves like a newborn baby. Okay, so this kernel stack is here now. Now the thing is, when the child gets scheduled, where from it starts, it pops the system level context, I mean the user level context, and to resume its execution. And when the parent process starts, I mean gets scheduled, it will again pop the user level context, because it's just like waking up, getting returned from a system call. It will resume its activities. So this is how a parent creates a child. So the story is a bit long, but this captures the entire philosophy of how processes are getting created and they are maintained by the system. So this is the entire story. So if this part is clear, this figure is clear, I think rest of the things, I mean throughout the process management will be more easy to, you can relate it. Maybe it is thread or signal handling or whatever it is, file processing, whatever. Okay, so if you have any question till this point, you ask me. Otherwise, I'll switch to the examples of fork now, because this part is extremely important, that you have got a clear conception about how a process is maintained as it's a dynamic entity. Do you have any questions?
Sir, do we
Yes.
Sir, do we copy the stack segment and the code segment? This segment, do we make a copy of these segments in the
Yes.
memory?
Definitely, make a copy.
Sir, okay. So they both have their own segments, right?
Yes,
Sir?
I'm coming to that. Yes, that's true.
Okay.
Definitely,
okay.
Because I mean I have not made it more clumsier looking, but again, uh, uh, here you have got
Yes, sir.
this step. It's like, just focus on this. Make a copy of parent context, means parent user context. So user level context means what? The contents of this text stack data and everything. So here I am showing the tables, and the tables are actually pointing to the pages, corresponding pages and all. Can you visualize that? So
Yes, sir. Sir,
these page map tables will be pointing, and the point is, say, if I'm coming to that. Here lies the confusion and the something that people messes up in the initial stage.
Yes, sir.
So the thing is,
So when
if the yes.
So when you copy these segment map tables, if
Hmm.
you copy the contents, it will point to the same stack
No,
and all.
that's the point.
And
It is not. So that's what I mean. So this is not copying. These contents are not copied here. So they have got. So the point to note is these contents of the tables are not copied. Rather, it will create a copy of the actual pages in the virtual space, and this, and wherever they are loaded, partly loaded, so that information is
okay,
maintained here.
okay, sir. Okay, sir.
So I mean this is for all others who are not asking the question. This creates an ambiguity, because I could have shown that also. It would have been more, so many blocks and all this. People would have been messed it. So try to understand that these tables are not copied. If it have been copied, that means both the parent and child are pointing to the same code. That's fine. This might happen because code is not going to be changed. But they should not point to the same stack or the same heap or the same data segment, because that will be dangerous. If the parent changes the child, if the parent says that I'm incrementing my local variable, the child also will get affected. That should not happen and never happens. Okay.
Okay, sir.
So I mean, so the point is, the code segment, you see, it's basically a read-only segment. The code segment, which contains the executable code, CS. So the CS, sometimes in some implementations, the CS is basically shared. Okay. So CS is shared, and both can point, but in the other segments which may be modified during execution, those are not shared. And in fact, to save this, I mean, there are certain issues to make it efficient and all. So instead of making duplicate copies, so copy on write and all this, so those things are there. I am not going into the details. So right now we assume that these tables, the number of tables are the same, but the contents of the tables are not same even after BART, because the child will now have its own code segment and the parent will have its own code segment. However, the contents of the both will be the same. Child will have its own user stack, the parent will have its own user stack, but they will have, uh, although the contents will be the same after the fork, immediately after the fork, they will have independent copies. Okay. Is there any other question? Okay, then now let's look into this very simple code. Just go through the code first. Try to understand the code. So this is a fork call, and this is, say, this is a process, and this is the parent process, say, for example, and the parent forks a child here, and we have because this fork returns something as x is treated as, declared as PID underscore t, which is a special type holding the PIDs defined in the systypes.h, and stdlib actually uh, stores this fork and all this. So here what it means, these are the, so what is this I and x? These are local variables where they will be stored, these two local variables. Which segment? This I and x, these are local variables. So which segment in the parent process they will be stored? Hello? Hello? Are you getting me?
So the data segment.
Why data segment? It's a purely local,
No, no,
it's
no,
a
sir.
local to a
The
function.
stack segment,
Stack
sir.
segment. Yes, the
Yes,
stack
sir.
segment.
Stack segment.
So in the stack segment, we will find that there are entries for I and x, and they are to be maintained. And this entire code, where it will be found? Which segment? In the code segment
Code segment,
of
sir.
the parent. And when you say it's a stack segment, now you have to differentiate which stack, user stack or kernel stack. I and
In
x,
the
which stack?
user stack, sir.
User stack segment, because the kernel stack will be used only when you are executing fork and all other system calls, printf and all this. Okay. So it will have different things. It will have the context of user, the context of different system calls saved as it executes. Okay, so now what you can see here is at this point so these two will be executed purely by the parent, this initialization everything, and this statement will be executed by the parent, and once it executes it will create a child, and the child, as we found, what will be the code of the child, what will be the contents of the code of the child in the so
Same.
child's code segment will be same as the parent's code segment, right? So it will be kind of exactly the same, it will have a copy of that. But the point is this fork returns what? Fork returns the value. So now you see that once it is forked, you have this black and another black, like this is a child process, parent process, and the child process. Now the parent process, after it has returned from the fork, it will receive what? The ID of the child. And the child process, after returning from the fork, it will receive what? The value 0. Now what we wrote, if x is greater than 0, then you do this. So when x will be greater than 0, only for the parent. So the parent process will be executing exclusively these two statements, and the child cannot execute this the way we wrote it. But in the else part, if it is not greater than 0, it will be 0. Hopefully there is no error in the fork, otherwise it will be -1. So if the fork is correct, then for the child it will be 0, and it will be coming to the else part. So these two statements will be executed by the exclusively by the child process. Okay, so is that clear? So just we can create distinction among the code, although the contents of the code is the same, but we can make logical distinction about which portion of the code will be executed exclusively by the parent and which portion will be executed exclusively by the child process. And if I write after this if else, if I write this printf hello this one, so who is going to execute it?
Both, sir.
This last printf, because you see if it is 0 or greater than 0, because there is no condition before it, so it will be executed by hopefully by both the parent and child. So the point to note is both the parent and child, once the child is created, both the parent and child will have the same piece of code segment. The content will be the same, but because after the fork the return value in the parent and the child differs, one is non-zero, one is 0. If we want, we can create distinction in the code, logical distinction in the code. So make sure part will be only by executed by the parent and the child, however this part will be executed by both of them. This is possible. Now can you get output of this code, although it is already provided here? What will be the output of this code? Okay, let's look into it. So this is the parent process, this is the code of the parent process. So it was executing this I equals to 5 PID underscore T. So there is no question of having the child, it's just the parent we have executed. So when it is here, then it will be the in the stack segment we have entries for I and X, this I and X local variables. What is the value of I? It is 5. Value of X, it's garbage because we have not assigned anything. Now and logically if you look into it, so this portion will never be executed by the parent because it's a parent process. Now once it executes fork, suddenly the child process got created, and the whole story we just now uh, listen to the story how the whole thing got created. And yeah, we are not actually showing the entire details. We know that everything is there, all the process map tables, I mean the page map and segment map tables, the area, the process table entries, then the file table entries, file descriptors, everything is there. But we are actually now focused on the actual code execution, what will happen, and basically the user part of it, because it's a user level application and we are just focusing on that. So that's why I discarded everything else and just have shown that this is a parent process, the virtual space of the parent process, and this is the virtual space of the child process. And in the virtual space what we have got user space. Okay, so we have got the data segment, keep segment, code segment, and the and the stack segment. And the child also has been created from the parent. So initially, just after the creation, it will have the code segment definitely be the same, data heap and the stack segment. So the question is, just after the creation, if the child wakes up, so as you can see, after the fork, x is 46. So what that means, what is the PID of the child got created? What is the PID of the child that the parent will know? It is 46 because this is x. And what the child will come to know? I mean, so the child got copied everything got copied, but it's independent copy. So CS of parent, CS of child, DS of parent, DS of child, SS of parent, SS of child. So you just copied these stack contents here, so it will be exactly the same. But will it be 46? What will be the value of this x in the child? What will be the value of the x when the child returns from the fork? What it will
0,
see?
sir. 0.
0, because the child will, so that is how it returns. So you can think of that when the child is about to return, the kernel will make sure that in the U area there is a field where you store the value returned by a system call, and there it will place 0, whereas in the parent it will place the value of the child just now created. That is how it it supplies the value, so that the child and parent both wakes up and find those values, and it basically copies into x, so x gets a copy of that. So the child will never be able to see and execute these portions, of it's of no use for it. So now if I keep scheduling, so only one at a time it will be scheduled if it is a uniprocessor system. So now maybe that after this fork which the child got created, now this yellow line shows the current execution statement of the parent. So the parent executes I plus equals to 5. So what will happen? Can you see the change? It's making the change where? In its own stack. And does it impact the child? Child got the copy, but the child is maintaining its own copy. So initial value of this I is 5 because it got it copied from the parent. But now from now on, whatever the parent does with that value of I, it's local to its own stack, user stack, and it is not going to affect this child process's user stack. Is that part clear? Is that part clear?
Yes, sir.
Then maybe that still it has got some time and it executes a printf statement. What is this? What do you expect from this? I would expect parent process because it is exclusively for the parent. So I says parent process. I'm trying to display the PID of the parent. So I just call get PID. Get PID means the parent wants to know its PID, it displays it. The value of x also it wants to display. Right? So after getting displayed, hopefully so we get a display from the parent. And then after that, maybe that there's a timer run out. The parent got got into the ready queue. Definitely after executing the printf, and then the child got scheduled. Now the child will never go to this. It will find that it is after find that this is false. It will come here. It will increment the I. What will find? So the first execution is the I plus plus. It finds that it has incremented from 5 to 6. This x is still 0. It never cares for that. Now then it executes printf. What will display? The child process ID. Its parent ID. So child process ID is get PID, parent process ID is get PPID, and the value of I. So this will display from the child. Now after that, what happens? Who gets scheduled? Because now both are independent process and both have their independent, contents, user area contents, user space contents, segments, and all. So who will be executed next? Which process out of this parent and child? Who gets executed now? We cannot say because the scheduler, we don't know. There are many other factors that comes that we'll examine later on. Let us assume that after that parent gets executed. Now parent will execute this because this statement is not having any check on the value of x, and it will display hello with its own PID, and then after that it terminates. Then comes a child, and the child also will execute it. is not, it's not having any checking, so it will also display hello. And so because of that, what is the output of this? Output will be this one. You see, it is executable of that, of this particular code. I have compiled it. Then I writes a parent process. This is the parent process ID. This is x equals to 10, and then it's hello this. So parent process successfully, means maybe this is the case that the parent process is not getting interrupted, because while the parent is doing this, is the child alive when the parent is executing this? By the time, is the child also ready to run?
Yes, sir.
Hello. But probably the parent got scheduled, whatever is the reason maybe. And maybe we can also see that the parent keeps executing the statements up to hello, and the timer is set to such values, or the priorities are in such a way that it never gets interrupted in between, even through the timer run out, because these are very trivial statements, so it will just get executed in a, you know, in a flicker of a moment. So that's the point. Now after it gets completed, then there is no more other user processes, then the child gets executed, and the child displays its PID, its parent PID, and as you can see that, so this proves that this was the parent of this child. So this parent created this child, and it increments by the time it has incremented by ++1, and it is displayed, and there is hello 130. Now this might happen that I mean, in some cases, if there are too many number of processes running and we don't know what happens, so this parent process comes, displays this, then the child process display comes, then this hello 129 comes, then hello 130 comes. That also may be possible. Or you can think of like parent process, this comes, then this child process statement comes, then hello 130 comes, and then hello 129 comes. So anything can happen. So this is not the only possible, but again, if you keep running this, and probably this is what you get out of it. And what I can do here, if I add a small sleep here, if I add a small sleep 1 second, then what do you expect? If I add a small sleep statement here,
So
then I am
timer
forcing
run out.
no timer. It's not timer run out. I am giving a sleep. I am forcing the parent to sleep, suspended. So parent is getting suspended for no reasons. I'm just the parents willingly suspends itself. What the point? You prefer to sleep for a while. You set an alarm, so after 1 second you will just you will be awake. So the point is, by the time if the parent sleeps, definitely the child will take turn and will keep will do its own job. So if you give a sleep statement here, the child process this executes, and then after 1 second the parent comes and the parent executes this. What the point? So if you look into this, I'm just commenting these two. Can you see the screen right now? Is the screen visible?
Yes, sir.
So here you see, I would like to, so this is just forget about these two steps. So if I just write a sleep, okay. So this is what it shows. Oh, the fork was gone. So one fork should be there. Fork, this is X. So the same code, I'm just showing it. There are some warnings, let us ignore it for the time being. So this is what happens. So parent process executes 199, child process 192, it's just parent, the child. Now you see that has happened. When I took the snapshot, you see, now you cannot guarantee what is going to happen. Now the parent process executes this part, then the child process got scheduled, and child process got hello, and then this comes. So got the difference? But earlier, you see, earlier it was parent and hello like this. So nobody knows what is going to happen, in which sequence it will be executing. And if I give here %b, comma get PID. So who has executed hello first? In this case, which process, parent or child, executed hello first?
Parent,
The
sir.
parent and then the child. But just now you found that it was basically probably the child got executed first. So this nobody can guarantee what is going to happen. Now you see, so this is again the same. Now that small change, if I make a sleep here, sleep 1 second. So whatever you write here, this argument of sleep, this is treated as the number of seconds that you want to sleep. So who is going to sleep now? This parent process wants to sleep. It increments, but it sleeps and then it displays. And meanwhile, child might take the chance for execution. And this happens. You see, child executes, even displays a hello. Then the system waits for a while because 1 second is too much for a CPU execution. So it waits, gives a pause, and then parent process schedule, and it just, so you see 1 second. Waits. So the child process executes, waits, and then the parent process comes. Got this? So now is that part clear? So even though you see both are sharing the same, it's not sharing, both are having the same piece of code in execution, and as the parent process has declared these two as local variables, local function variables, so they will be stored in the parent's stack. When the child gets created, it will be also copied in the child stack, but they are independent. So if the parent increments it by 5 and the child increments it by 1, so that gets affected. So you will see that this is 6 and this is 10. So now they are doing things independently. Is that fine? So up to this, is there any question? So just tell me a few small answers and then I'll end the class. So what will be the output of this? How many times hello will be displayed here? Tell me the answers.
2 times. 2 times.
Sir.
2 times.
2 times. Why 2 times?
Sir, one parent, one child.
For child.
See, the point is both the parent and child will execute this. So after the for, so I mean, I'll just discard the rest of it for sake of simplicity. So after the fork is completed, so both the child and parent, because there is no if condition and all, so you just ask both of them to execute what? Printf hello. There's no checking, so just printf. And from the return from the fork, both the child and parent returns on the fork and displays. So how many times hello? 2 times. So this is trivial. Okay, so let me just modify it. And this will be very simple. So I think two hello, that is fine. Now what about this one? What will be the output of this?
So 4 times.
How many? 4 times.
3 times, sir.
Sure. Huh?
3 times.
How many?
4 times.
Are you sure? Any other answers? Now now start applying your understanding and also intuition, because this is important. So try to visualize the code. The code looks to be very simple, but the thing is, now which part the parent will execute, which part, now there are multiple child processes, so just try to think of it. Say
4 times.
Yes, sir.
How many?
4 times, sir.
4 times. So let me see. Say this is a fork. Say this is a fork one. This is the first fork. Say for example, this is the first fork, and this is the second fork. Okay, so there are two forks. So if I write here, this is the first fork. Say F1 means first fork. So when this gets executed, what happens? You have got so this is the original parent process, and this is the child of the parent process, the first child, right? This is the original parent, and this is the child of the first parent, first child of the parent. So this parent, when it after executing the first fork, what is going to do? The original parent. After the first fork, the parent has created this child, and what will do next? After creating the first child, this parent, the parent has already executed this one. So the original parent is going to execute. What is the next statement following the first fork? It is the
So it will execute the next fork.
second fork. So parent will execute the second fork. So this is the F. I don't know when those markers will come, and I think others they are having some tools, but I don't have any tools to show. It's a problem. Okay, so this is F2. So the parent now executes the second fork. So second fork, what it will create? Second fork will have one line through which the original parent is getting executed, and it will have another child got created. What is that child? C of you can write C of 2. The second child of the parent got created. Is that fine? So then after getting out, after successful execution of the fork 2, second fork, it's a second fork, what the original parent will do now? What the original parent will do?
Print hello.
So print the state, execute the print statement.
Hello. So hello will be printed.
Execute the print statement.
That's it. So the printf hello will be, this will be there. Now this is done. So this is one way. So parent creates calls the first fork, creates a child, is goes on creating the second fork, executing the second fork, creates another child, and then it executes this one. Fine. So now let us come to the second fork child. Second fork child. So second fork child, at what point it will start? From which statement it will start? The second fork child. Can it execute the first fork? This child, second child of the parent, will it be able to execute the fork 1?
No, sir.
Because it has been
sir.
created through this statement. You see, it has been created through this statement. It cannot never go up, although it is there in its code segment. Okay, you don't have to distinguish it using x greater than 0 less than 0. It cannot simply go up because it can only come down because it has been created through this. So what follows next to it? The child. What it will do now? Second child. It has been created from the second fork. So what follows next?
Print hello.
It's a printf statement. So it's basically the hello. Is that okay? So now let's come to the first child. So first child, where it was there? First child, if it is getting, maybe it has got scheduled right now. So where is first child? After the fork. After the fork. So first child also is here. So what will be the next statement executed by the first child of the parent? No, which fork? I have distinguished
second fork.
one and second fork.
Fork.
Second
So this will
fork.
execute the second fork. So this is safe too. Okay. So now once this is executed, so what will happen? So it will have the original. So who is its parent? So it is the child, the first child itself, and it will create one more child. And let us call it as say this is the C1. So we call, let us call it as C1. Okay, this is the first child. So this is called it C1. And what it creates here, it is C of, it is the first child's first child, like kind of. So C11. So it's the first child of the C1 process, or I mean C1 child. Is that fine? And this is the original C1 child itself. So after calling the fork to the first child, what it does after calling fork to the first child, it executes. Hello, it will execute. Okay. So what next? So which process is now having? So it's only having C11. So from which fork it has been created? From fork 2. So what will be the only statement that it is going to execute? It's a hello. Okay. So how many hellos will be there?
So 4.
So we have 4. So I've given 2 forks and a hello. Rest is just commented. Okay. So let's see. Got it? Got it? So who was telling three hellos? Did you find what was wrong?
Yes, sir.
So it is better you try to visualize at least initially these kind of tree diagrams. Otherwise, it may be you may end up with errors. Can you now? I would expect a correct answer from all of you. How many hellos? So this is ORing, fork or fork. First of all, will it work or will it give a compilation error? Can I write this statement? It will work. I mean, syntactically it is fine. So if it works, then how many hellos will be displayed?
Sir, 3, sir.
So 3.
3. So you have to now apply your the very basic understanding of and say ANDing, ORing, and all this logical operations. Okay, so if in a if in a ORing, if the first statement, I mean this first statement, if it is true, will you execute the second statement in an ORing? If the first
No,
is
sir.
true, then definitely it will be true. So it will not actually, it will never go on executing this one, and that remains apparent. I mean, that you can feel here. But if it is false, then it makes an attempt to check if it is true, because if it is true, then also it will be true. But if the first one is true, it will never check and execute this one. So although you have written 2 forks, it will be actually executing 3 of them, not all 4. So that's why there will be actually 3 processes. So if I still write this, so it will be F1. It becomes very difficult to write. So others are you getting? All others? Other students?
So
Yes,
for now you can use
parent.
Microsoft Paint, sir.
Yes, sir. Yes, sir.
So
Hello?
for now you can use Microsoft Paint for writing.
Microsoft?
If you don't have any scribbling. So if you don't have scribbling tools, then you can use Microsoft Paint.
Paint.
We'll do the
Okay.
task now.
Yeah. Yeah, that is possible. So if it is, it's just like a whiteboard. F1, then you have got this parent, and the parent executes what? Now these are first fork. So this is the first fork and the second fork. This fork or fork. So it's the first and this is the second. Is it visible in the screen?
Yes, sir.
Okay.
Yes, sir.
So this is P. So this is original parent, and it has already created a child. Child means the first child, say for example, out of the first fork. So the parent, what it will receive after the first fork, what the parent will get in return?
Sir, the PID
It will be returning the PID.
of
So
the
PID
child.
means it will be
Of the child.
a non-zero value. So any non-zero value will be treated as true, right? 3, 4, anything is true. 0 is only considered to be false. Is that fine? In logical expressions?
Yes, sir.
So for the parent, this will be true. So the parent is not going to execute F2. Is that okay? So the original parent is not going to execute F2. So there will be no F2, and what follows then? Otherwise, you have to basically display hello. So this will display hello. But this child, the first child, when it wakes up, when it returns from this first fork, what it finds? It had received
0, sir.
0. So definitely the child itself will go and try to execute this F2. Okay. So this child executes F2. What happens? So this is, say, the original child which executed fork 2, and this is what? This is the child's child. So child C1's first child. So after executing this F2, what the first child will do? Nothing to do. It will display hello. And the second child, or the first child's first child, C11, it also gets returned from this, and what it receives? It receives 0. Doesn't matter because it has nothing to do. It will come down and display hello. So what is this? How many times? 3 times. Okay. And if I write this, this is.
So there are 3 fork statements.
This should be commented here. For asking the question, I have shown you the result. So, is that okay? It is just 3. If it is ORing, it is 3. If it is ANDing, what will happen?
So 3.
What will be the change in the result?
It will be 3.
If it is ANDing,
So then 2 only. 2.
are you sure?
Yes, so it should be 2.
Just take a minute of time and draw it, because I have already illustrated it. I hope that you people got it.
Sir, in AND also 3
If it
will
is
come.
ANDing, what will happen?
In
So
AND
3.
also 3 will come, sir. Same concept.
How much? 2.
3.
So 3.
So I'm not getting your names because I'm in the full screen. So who was telling 2? Have you got this? Why it is not 2? I cannot see the names. So are you getting why it is?
Yes, sir, yes.
See the same thing. So just like how it will look like. In that case, how this branching will look like? It will just be like this. So it is F1, and it will have this. P will execute here C1. So I mean this is C1. But here, even though, because it is ANDing, so the parent, even though it is true, it cannot stop. Rather, it should go and check for the second one to make this whole expression true, right? So it will be, because it is true, it will go and execute the F2 here, and thereby it will have its own execution, and also will have the C2, the original parent C2, right? However, this first child, once it receives 0 here, it will not be interested in executing the second fork, because in any way it will be false. Is that correct? Hello?
Yes, sir. Yes, sir.
So this first child in this
Yes,
case.
sir.
So this will immediately, it will not execute this, and it will immediately display hello, and these two definitely will display hello. That's the case. So it's just like in the ORing case, it will be like this kind of left heavy, and the ANDing case it will be right heavy. Sorry, just reverse. Got it? So now can you tell me the result for this one? What will be the result output? Quickly.
So 6 times.
How many? 6.
6 times.
What will be the result for this one? How much?
Say 18.
Sir,
How
18.
much here?
36.
36.
46. So it's basically you can think of something like this. There is no marker possible, no? Here. No, you cannot edit. So anything that, so you can think it like this. So anything that follows a first for will be executed twice, right? So this portion will be twice. Anything that is executed below this will be how many times? This also will be twice of twice, something like this. So you can consider it like this. So if it is the outer fork, then the first fork, the second fork, then the fork. Those who are getting it's fine. For those who are still having confusion, just try to follow and see that. So you can always draw these figures to make it clear, but it becomes too complicated. I mean, too many branches once it is having too many for loops. So I say that anything that is following the first fork will be executed how many times? 2 times. Anything that will be following this fork will be executed how many times? 2 times. Anything that is executed within this, I mean, following this one, how many times?
3 times, sir.
3 times. And anything that is following this one will be executed how many times? 3 times. Okay. So if you nest some hello statement here, I mean, nesting means if you write some hello statement at the end, so this will be 3 times of 3 times of 2 times of 2 times, something like this. Now got this? Everybody got this? So now you don't have to actually draw it or check it. This will be obvious. Yes. Okay. So that will be the end of today's class. So we took the example of we took the pseudocode of fork, how to create child processes, and that is I feel it's one of the most interesting part of the operating system, how you create a new process and what ways it manifests its existence right from the right from its birth, and how it gets the exact, it becomes the exact copy of its parent, but once it starts working or functioning, it can always be treated as an independent, I mean, it is an independent process, and it can always have its own way of execution. And to make distinction of what the parent and the child which is created by the fork will execute, you can always use the return value of the fork, and using some if else statement, or there are many other ways to create this logical distinction. We can do that, and we can still make some portions which is common. So you can simply play with the code, and there are several examples that I'll give, so you can write those statements, and it can be really something. At times you have to look into the code, that how it works, and so that is something important. So and we took some examples where we took a combination of forks and found that how many times it gets executed, what is the execution sequence, and all these details. So just one assignment, I've not yet typed it. I'm trying to do the assignments for some time, but yeah, not having. I'll do it. So one just assignment. I think everybody can listen. So the assignment is like this: you write a parent and the child. So no matter how many forks are there. So the way we are displaying manually, that this is that kind of hierarchy that gets created. Hierarchy means right from the parent process, the child, and all this. Now, just writing the code, can you create the hierarchy? Can you display the hierarchy at the end? I mean, or may not be the hierarchy. Can you create a file from which you can, draw a tree of this process hierarchy rooted from the parent? Are you getting my question? So the parent process forks a child, maybe once or twice or whatever. Now, once it is done, then the child process and the parent process both will be, the idea is they both create a single file. I mean, the file the parent can open, the child will also be able to share the right mode. So now whenever the parent creates a child, it dumps its child id in the file, that I am the parent and this is my child. So everybody does it. So every parent, whenever it creates a child, it just says that I am the parent and this is my child. So if I dump it, so whenever you create, you just dump it here. That's your first step. If you do that after the process is complete, okay, so the original parent, if I ask it that now if everything is complete, now can you display in a level wise format the parent child hierarchy? Can you do that? A common file they will write, and you yourself also can open that text file and see that what has happened, and you can manually also draw. Is that possible? You can have some variations of this. I'll just put it in words. So the thing is, the parent creates a child. Now the simple logic is, if the child feels that his id, the child processes id, listen to it, the child process id is even. If it is an even number, the child will go on forking one more child, another child of it. If it finds that its PID is odd, it will not do it. Got the point? So the logic is something different. So we can have nice visualizations of this. So the parent creates a child. If the parent processes ID, even including the parent itself, if it is even, it will create one more child, just one more child, and its child also will do the same. If any process finds that my PID is even, it will fork one child. If it finds that my PID is odd, it will not do any forking. So once you do this in this fashion, and how many times I do it? Maybe I do it for maybe up to level 10 or level 5, and I would like to have the entire process child hierarchy. Okay, I'll discuss about it in the next class. For you all, can you give it a try? That whenever the IDs are created, the process child is created, open a file and just try to share the store the information of child and parent, and just open the file and see that what has happened actually. Try to do this. In the next class, I'll be talking about some kind of issues related to files when the parent is having a file and a child gets shared access to it. So we'll see that how it works. I mean, what sort of issues comes up. Okay, that will be the first topic. Then after that, we'll be talking about signal handling. Signals we talked much earlier. I mean, in one of our class, I think the last class, we talked about signals. So we'll talk about signal handling in operating system, how a process can send a signal. It's extremely interesting, and it's very easy to use also, but it is very useful. You will see that nice magical things start happening when you keep sending signals, and at some point of time your process is running and suddenly a signal came which you actually wrote that it should be triggered at this point of time, setting kind of alarm, and the process does something different. Or we can do something like from the keyboard, there's a background process. From the keyboard, I keep pressing or there's a foreground process. I press Control C, but you find that the foreground process cannot be killed. Generally, a foreground process when it is running in a finite loop, if you press Control C, it can be killed. But you can make some arrangements that when you press the Control C, the foreground process will never be killed. I mean, will not be killed. And you can make such arrangements that you press one time Control C, not getting killed, two times not getting killed, three times getting killed. So it's just like you can make provisions that how many times it can escape, one, two, or three. So these nice things can be written if we know signal handling. So in the next class we'll talk about signal handling. Okay, is there any question? Hello, any question?
Sir, will it be possible for today's extra class to be shifted on Friday? On Friday we have like a schedule, means a slot empty. So if this class will be shifted on
Yes,
that slot.
I don't have any problems because you see this course is having 150 students and 3 faculties are trying hard and trying their best to get slots. It's also a kind of resource problem like the operating system. So directors are, you know, that we cannot just talk. I mean, if he is willing, we have to give him classes. But
Yes.
and Onimesh is also willing to take the class. But in my case, what I find, I need at least 2 classes per week as per my plan. I can share you the lecture plan. So if that is not possible, it will be difficult for me to complete because there are a whole lot of things, including IPC. So it is not complete. It will not be able to complete. So one class, if I take, if I can manage to take, say Monday or Wednesday, another class Friday is good enough. But if Onimesh takes a class in Friday, I don't know how you manage another slot.
Sir, on Friday from 4:30 the slot is empty, so you can take today's extra class on that time slot.
Okay. Fridays.